Hello everyone, my name is Mathieu Gonzalez, and I'm going to present to you TwistSLAM, Constrained Object Tracking and SLAM, which was written with Eric Marchand, Amine Cassette, and Jérôme Royan. So the goal of classical SLAM is to estimate a map of the scene and the sixth of pose of a moving camera using only visual information. So we can see here on the left a video from the Kitty dataset, and on the right the output of the SLAM system with a set of 3D points that represents the map, and in green the pose of the camera. The classical SLAM algorithms are limited by the static scene assumptions. So when objects move in the scene, they can corrupt the map, as we can see here, and can decrease the accuracy of camera tracking. So in this paper, we propose TwistSLAM that can estimate the map of a scene and the sixth of pose of a moving camera similarly to a classical SLAM system, but can do so in dynamic scenes and can also track dynamic or potentially dynamic objects in the scene using only visual information. So we can see here that we are able to track the cars, estimate their speed, and update their pose in the map below. So how can we solve the problem of the static scene assumption? We can compute the semantic segmentation of the image and hide potentially dynamic objects, such as the car here, and feed this image to a classical SLAM system. The problem with this approach is that it removes potentially dynamic objects that could be in reality static, such as parked cars, for example, and this can decrease the accuracy of camera tracking in some scenarios. The other problem is that we lose an important piece of information that can be useful for some applications. So, for example, self-driving cars may need an estimation of the trajectory of pedestrians and other cars in the scene. So what we propose to do is to use the potentially dynamic objects that have been segmented to do object tracking, and then to fuse both camera and object tracking in a single bundle adjustment to refine everything. And this way, we can take into account dynamic objects. So, for example, if a car if a car speed has been estimated to be close to 0, its 3D points will be used as static points. So, more precisely, in our approach, we propose to track clusters corresponding to objects by estimating their twist that correspond to the velocity of objects and to constrain the twist. To do so, we represent the world as a graph of objects and use the static clusters such as the road and the wall for camera pose estimation. And we track the remaining objects using mechanical joints. So for example, here between the car and the road, we have a planar joint that forces the translational speed of the cluster to be parallel to the road and its rotational speed to be perpendicular to the road. This way, we obtain a displacement that is coherent with the scene. So how can we do that? Well, if we simply estimate a twist that is not constrained, we can obtain a twist that is not coherent. To constrain it, we propose to use a projection operator pi and to project each component of the twist so that it is coherent with the plane that has been estimated. This way, when we update the pose of the object, it will keep to be coherent with the structure of the scene. So for our pipeline, first we extract key points and use static key points for camera tracking. Then object key points are used for object tracking. Then we segment the new keyframe and use the segmentation to create new objects in the scene. We estimate the planes to constrain the movement of clusters and refine everything in a single bundle adjustment. So first of all, for camera tracking, we simply minimize the reprojection error of 3D points belonging to static clusters. Then for object tracking, we optimize twist by updating the previous pose of objects. When we do so, we update freely the object pose. So instead, we are going to project each twist using the projection operator that we defined. So an example of projection operator is this one in the case of a planar joint. And we can see that when we multiply this projection operator with the twist, we obtain only a suite of twist that has only translation possible on the X and Y axis and a rotation around the normal of the plane. Then in the bundle adjustment, we optimize all camera poses and all object poses by respecting their constraints and apply a constant velocity constraint on the twist so that the trajectory of the clusters is smooth. We did several experiments on the kitty tracking dataset and showed that camera tracking accuracy was improved with our approach. We also evaluated object tracking accuracy and showed that compared to TwistSLAM 2, we obtained a better tracking accuracy. We show here an example of what happens when we have no joint constraint on the car. We see that the translational part and rotational part of the twist are not coherent with the road. However, when we apply our planar joint constraint, we can see that the translational part of the twist is parallel to the road, and its rotational part in blue is perfectly perpendicular to the road. We show here another example on the kitty tracking dataset. We follow a car that slows down and then stops. We can see that we correctly estimate its speed and update its pose in the map below. When its speed is estimated to be close to 0, its points will be used similarly to static points in the bundle adjustments. We also show here that we are able to track at the same time a cyclist and a car that moves. We can see that their speed is rather coherent and that their trajectory in the map below is also smooth and coherent.